Hello everyone, my name is Aaron Standard and I'm one of the creators of Akka.net, and today we're going to talk about what I've spent the past month working on. I wear a lot of hats. I'm a business owner and we've got employees, we've got customers, we've got a big open source project, Akka.net. There's always lots of stuff going on. Since about June 27th, I have spent 70 plus hours tracking down a single bug. And while this was happening, everyone in my family got COVID. We got hit by a hurricane here in Houston. It's been a month. This video is mostly meant to entertain, and it will educate you a bit on some of the techniques and lengths we went to go and find this bug. You'll learn a bit about distributed systems and how to use open telemetry to go ahead and track down really nasty emergent behavior that's difficult to reproduce in a lot of cases. And this is the story of the hardest bug I've ever had to fix in my career. Now, I've been working on Akka.net, which is a distributed actor model implementation. I've been working on it for over 10 years. I've had to track down lots of nasty distributed systems bugs, race conditions, consistency errors, all the different types of classes of really hard problems to track down. This was the worst by far. So let's go ahead and actually dive into the details of the bug and talk a bit about what went into finding it, what exactly was the bug, and how did we eventually end up fixing it. So there were two bugs that were reported last year, and last year and this year, in the past 12 months. The first bug was a duplicate shard bug. Now, I'm going to explain what that means for people who are totally unfamiliar with Akka.net. But the basic gist of this is that Akka.Cluster.Sharding is the highest level component in Akka.net. It's a way of being able to guarantee that even in a big network where many Akka.net processes are all connected, that there will be guaranteed structurally a single instance of each entity actor. So if you have an entity actor that represents some real world entity, let's say we're doing an Internet of Things system, each one of these actors represents some device on the network we're monitoring. Akka.Cluster.Sharding guarantees there will be exactly one copy of that, even in the event that our network gets partitioned as a result of, let's say, network disruptions somehow. So in the event that we have, let's say, some nodes that we can't communicate with, we guarantee there will still only be one instance of that entity. Well, the problem that got reported was that there were, in fact, cases that multiple customers were able to reproduce where there could be two copies of entities simultaneously inside our system. And it was even worse than that. It was actually two copies of the shards. The shards are the things that create the entities. These are the parent actors in the ecosystem. So the fact that there could be multiple shards means that there could be multiple conflicting different instances of entities running around simultaneously for a prolonged period of time. So that was bad. That was the first issue. Now, we explicitly test for scenarios where shards are being transferred between nodes as a result of scaling the cluster up, scaling the cluster down, redeploying software with a new version, all the different things that might happen in like a live production system. We have what we call a multi-node test runner that allows us to basically run simulations of all this stuff as part of Akka.net's normal test suite. And we test for a lot of these scenarios, and none of them were able to reproduce this bug or had reproduced it at any point over the past 10 years or so. The other issue that got reported was an unexpected Singleton movement. Akka.Cluster Tools is a library that Akka.Cluster.Sharding depends upon, so it's a dependency of the sharding system. And one of the components that it has is called an Akka.Cluster Singleton. A cluster singleton is designed to basically be a single instance of an actor, and there can only ever be one instance of that actor anywhere in the cluster. It's different than cluster sharding in that cluster sharding is designed to make sure that you have a distribution of entity actors, and there can be millions of those. With a cluster singleton, there's only ever one instance of it, like ever. And the idea behind this is that this cluster singleton is really meant for workloads that aren't very easy to run in parallel. So some examples of this include things like schedulers, or in the case of cluster sharding's coordinator is not something that can be easily parallelized. So the coordinator is the actor that makes decisions about where shards get allocated inside the cluster. So cluster singletons are only supposed to move when the previous cluster singleton is shutting down. This longtime production user reported that they normally organize their deployments to make sure that the Singleton node always gets updated last when they're doing a software update. Well, what they noticed was that the Singleton actually moved during the first replacement of one of their existing nodes in their live production cluster. They do a monthly deployment, and they've never seen that happen before or since, but they absolutely and provably saw it happen once. So that is a mystery as well. Now, one thing I wanted to iterate on real quickly is like, what harm did this bug actually cause? Why was it so important that we fix this? Why was it worth the effort we put into it? Well, this problem is what we call a split brain. And I have a YouTube video I just published to the channel called What Are Split Brains? Recommend you watch that for the full explanation, but I'll give you the short one here. This is like what a healthy Akka.Cluster network looks like here. This is a mesh network. Every node is directly connected to every other node. So it's a 6-node network. Every one of these nodes has 5 connections. In a split brain scenario, what happens here, and by the way, this is dealing with like Akka.Cluster and the Akka.NET processes itself. This can also happen with much more subtle issues like the allocation of shards too. But what happens with a split brain is it's kind of an insidious problem because it looks like everything's working normally inside your system here. But what's really going on is that we actually have 2 separate competing networks within our what appears to be one homogeneous network up above. So when we have the split brain happen inside our system, this is what the duplicate shards issue is really all about. The early Singleton move issue is slightly different than this, but the duplicate shards issue means we have a split brain. And when a split brain happens, we have a bunch of data consistency problems that occur, and this can be super harmful for a business. We end up with multiple competing variants of the truth of the system, of what's really happening right now. In the case of our customer who gave us the smoking gun data, they're a big IoT outfit. This would mean that some of their sensors and IoT gateway actors were getting completely conflicting pieces of information. Because basically what would happen is that 2 different actors would get half of the information from like an MQTT broker or something else, and therefore if they're only getting half of the data they need to do their job, they're going to start doing things that are unpredictable inside the system. So as a result of that, you're going to end up with really unreliable behavior. And depending on what your software does, this can actually be like dangerous, in some cases. So it's a credibility destroying bug. That's why this has got to get fixed. And that's why it's worth the level of effort we're going to put into it. Now, as I just went into a moment ago, these bugs are really difficult and insidious to track down. So that's the next thing we're going to focus in on is like, what did it take for us to actually try to begin investigating this? Our approaches, with using our automated testing system and everything else obviously hadn't worked. Our manual testing that we had done hadn't worked either. So it was time for a new approach. So let's talk a little bit about conceptually, what is Akka.NET doing and why are these bugs so harmful and dangerous? So the first, what Akka.Cluster.Sharding does. It creates a shard region for each type of entity we want distributed. So an entity could be devices in an IoT system. If we're building multiplayer video games, we might have multiple shard regions. One might represent a player character. Another might represent an NPC. Another might represent a zone that all these players and other NPCs and resources are in. And then you might have another shard region for things like let's say the chat that you have between players in a given area. So shard regions are just a way of being able to distribute entities in a even fashion across an Akka.NET cluster, and we guarantee that there will be a single destination actor for every single entity. This means that all of the state for a single thing can all get essentially co-located together in the same process somewhere. And this is what makes real-time stateful programming possible and easy with Akka.NET. And we have a whole video on cluster sharding that I'll link to in the description if you want to learn more about that. But this is kind of the quick version of it. We group entities into shards. Shards are basically just an arbitrary unit of distribution. And the reason why we do this is that you can have a really large number of entities, and not all entities will be alive at the same time, by the way. Entities will come and go as, if using our video game example, entities will come and go as players are active in different areas of the game. If you have, let's say, off-peak hours and there aren't very many players active, you'll have a much smaller number of entities than you will at peak hours, where there's much more people active. Well, What we do in order to make it easy for the sharding system to reason about where is stuff located inside the cluster is we go ahead and we group entity IDs to shard IDs. And we typically use a consistent hashing scheme to do that. And then we have a video on that too that I'll link to in the description. But basically this means that instead of having to reason about millions of different entities, which would mean that our state for managing where stuff is inside the network would be quite large, instead we might only have to reason about 100 shards or maybe 1,000 shards. So we can kind of scale down the amount of state management the sharding system has to do by 1 to 2 orders of magnitude potentially. So that's what the shard ID is all about. Entity IDs are determined from the content of the messages we send to these actors, so we have to be able to extract an entity ID from each message we send through the sharding system. This is a little lightweight piece of C# code that you're going to end up writing if you use cluster sharding. It's basically a switch statement is what it is. Then we finally manage the life cycle of entity actors automatically. We start entity actors on demand as soon as they receive a message, and we terminate them usually by default after 2 minutes of inactivity. This is very similar to how Orleans virtual actors work. This is Akka.net's implementation of kind of that same idea of these sort of actors where they are started and stopped automatically for you depending on when they're busy. Well, one of the things we have to do in order to take advantage of, let's say, the dynamic nature of Akka.Cluster. Akka.Cluster is sort of our way of building highly available distributed real-time applications with Akka.net, is we have to have a process called rebalancing. This is where if capacity is added to the network as a result of scaling the system up, we need to have the ability to distribute some of the shards that are currently homed on our older nodes. We need to gradually rebalance them onto the new nodes. Likewise, when an old node is leaving, maybe as a result of a software deployment or as a result of scaling the system down, we have to very quickly rebalance those those shards off of the old node back onto one of the ones that's staying in the cluster. So sharding happens automatically behind the scenes. You as the end user do not need to do it. When the cluster is not scaling up and down, rebalancing does not happen. Rebalancing only happens in response to the topology of our network growing or shrinking somehow. A couple other things that happen during shard rebalancing that are worth pointing out is that when a node is joining the cluster, shards get gradually rebalanced. This process happens eventually. We don't want to move everything all at once because we actually pause network traffic to the actors hosted on shards that are being moved. We don't want to pause too much network traffic all at once because that'll cause a lot of congestion and it also will cause lots of memory pressure to build up if the system's pretty high traffic. So we prefer to kind of move shards gradually. So it might take a matter of several minutes for shards to be fully rebalanced onto a new node when it joins. That's intentional, it's by design, it's for safety reasons. When a node is leaving, however, typically nodes leave in response to, let's say, an external process management system like Kubernetes trying to shut an Akka.net process down because either we're doing a scale down, we're doing a redeployment, or whatever else might happen. Well, when that occurs, we do not have an arbitrarily long period of time to move stuff around. We actually are running on a clock that is owned by someone who is not Akka.net. Typically, it's going to be owned by cloud platform or Kubernetes or Windows or whatever. Doesn't really matter. But in any of those scenarios, when a node is leaving and has shards on it, we've got to get those shards rebalanced immediately. And this is the scenario, this leaving system, is where customers were reporting that there were duplicates occurring. It happened as a result of nodes being cycled in and out of the cluster. The diagram I have here is rebalancing when a node joins. We're going to run this process in reverse to kind of show you what happens when a node leaves. So if I have 6 shards, I have a shard region called items, and then I have an arbitrary number of shards. They're just numbered in this case, so shards 0 through 5. So 6 shards total. And then it has entity actors, which represent just letters in the alphabet in this case. Well, what would normally happen during rebalancing is that after this third node joins the cluster, we're going to redistribute 1 shard from host number 1, and then 1 shard from host number 2. And now we have an even distribution, and we're going to stop rebalancing at this point. There's a Singleton actor that's going to be running on the oldest node in the cluster. We're going to talk about cluster Singleton in just a second. But let's say it's right here, and it's called the coordinator node. The coordinator is the actor that makes the rebalancing decisions. It decides where shards should get allocated inside the cluster, and this is crucially important. there can only be one of them active in the cluster at any given time. What ends up happening is the coordinator notices this new capacity. We can see that these two nodes are much more heavily loaded than this one is. We're going to distribute shards onto that node until the distribution is roughly even again. That's the basic idea behind our shard allocation system. We want to encourage an even distribution in order to make sure that we're utilizing all of our resources effectively, so we don't have hotspots forming in the network. And also just from a safety standpoint, it's better to kind of spread our eggs out rather than keep them all in one basket. That's the whole purpose of the rebalancing system. So when a node leaves, let's say node 3 was leaving, we would run this process in reverse, where basically we would reallocate the shards back onto hosts 1 and 2. Same idea. So the other component that plays a really big role in this is going to be the cluster singleton system. So that coordinator I mentioned earlier is a cluster singleton. So imagine we have a 4-node cluster right here. Every node that is capable of hosting a cluster singleton will be running an actor called a singleton manager. The singleton manager will only start the singleton once it determines that A, I am now the new oldest node in the cluster, and B, that the previous oldest node has completely terminated its singleton. So both of those conditions must be true in order for it to be safe for us to start up the next singleton. And this actor right here is a singleton proxy. This is basically like a pointer to wherever the singleton is in the cluster. It's able to follow kind of the communication that happens between the singleton managers, and it'll figure out where the new singleton is after it moves. So if node 1 becomes unreachable, meaning that it exited the cluster in like an ungraceful manner, it'll eventually get kicked out of the cluster and downed. Node 2 will now become the new oldest node. And once it knows it's the oldest, and if it's not able to contact the previous node after about 20 seconds, it'll go ahead and automatically start this new singleton down here. And the singleton proxy will point to it, et cetera, et cetera. This is how the singleton moves. Again, we have a lot of time padding and things we do in order to make sure, doubly sure that there's no such thing as multiple singletons active at the same time. This is all code that's kind of been around and has been in use by production customers for about 10 years. So all of this has been in place. That's kind of the setup for how those components work. The timeline of what got reported. The first thing is that we shipped Akka.NET 1.5 in March of 2023. Akka.NET 1.5 included really significant changes to the way the sharding system does shard rebalancing, especially if you're using the distributed data state distribution mode that's on there. DData is what we recommend now. This basically means that rather than needing to have a database to store information about how shards are being allocated, you can use the built-in in-memory, eventually consistent replication system that comes with Akka.NET. So this eliminates the need for another piece of infrastructure. So that's one of the pieces that happened in 1.5. So in about 6 months later, in late September 2023, we get our first email report from a user about duplicate shards appearing in the cluster. We open an investigation. We aren't able to really find anything conclusive while we're doing that, but then we get a second report from an end user in our Discord about the duplicate sharding bug appearing. And we also get a third report around this time. We do some investigation, we try to gather some logs, and we don't get a lot of concrete evidence as to what may or may not have happened. The one thing we do know is that all of these users are using 1.5 and they're using the distributed data mode for cluster sharding. So we suspect that maybe this was a problem that got introduced in Akka.NET 1.5. We basically end up putting our investigation on hold. We don't see any more reports for a while until we get this report on May 23rd, 2024, about 7 months later, that we basically get this report about the cluster singleton moving too early. And so I immediately think that these issues might be related. I do an investigation into this. I determined that one of the new settings we added for Akka.Cluster Singleton, allowing it to basically get rehomed depending on the app version, that could definitely be responsible for this bug, but it turns out the end user wasn't using it. So it's a false lead. So we end up not really fully concluding that investigation either. And then finally, about a month after that, on June 27th, we get smoking gun evidence from a paid support customer that the duplicate sharding issue is real and reproducible. The other evidence that we had gotten from some of our other users was a little bit more circumspect. We weren't able to fully determine was this just lag in their like telemetry system or their logging system? Was this basically an issue where maybe they had done something wrong or the cluster hadn't formed correctly? We didn't have a real good look at any of their environments. With this customer, who we have a kind of a trusted relationship with, we were able to see really clear black and white evidence that this problem occurred, and that not only were there two copies of this entity actor, but these two copies of the entity actor were both alive in overlapping periods of time for several minutes potentially. So we knew the issue was real at this point. So our initial thinking was that maybe this issue got introduced by Akka.NET 1.5 because all the bug reports occurred after that. Whenever you're maintaining software that's used by a lot of users, you've got to have a really good versioning strategy, and you've got to be able to use things like tagged releases and release notes to kind of understand what change made it into each version of the packages that you ship, or the versions of the software that you distribute, or the version of the API that you're hosting. We've had really good professional sort of practices around managing this for the past 10 years. So it's really easy for us to go and figure out where did changes to these areas get introduced. On top of that, Git and Git blame are also very useful tools for being able to go and look all this up. We knew that they were all using Akka.NET 1.5. We knew that we had made major revisions to the way Akka.Cluster.Sharding did shard allocation in that system. And we also knew that we had promoted distributed data as the primary storage mode much more heavily after that release. So we figured it had to be some culmination of those factors. Kind of mentioned that. Now, the other thing was that reproducing any of this was going to be extremely difficult. We had tried already during the previous instances to reproduce it and weren't able to come up with anything. We had a number of tests for being able to test cluster singleton leader handovers. We had tests for testing shard rebalancing. Some of those tests were racy periodically, but they failed for stupid reasons, not usually reasons related to there being outright duplicates. So we knew that there was a timing problem that was at hand for some of this. We also basically have data that we get from end users, but that data is not always super reliable. Data from users is often pretty incomplete, can be pretty sketchy, and a lot of the times users can end up doing things they shouldn't be doing. So a good example, we had a user who reported while we were in the middle of doing this investigation a duplicate shard, but it turns out they were running using Akka.Persistence as their storage mode, and they were using the default in-memory Akka.Persistence, which means that there's no way for the cluster sharding system to actually synchronize. So that would definitely produce a duplicate shard, but that's because the user's configuration was bad. So our approach to catching this bug was going to require us to try some new things. First, we needed to decide what would not work. So we decided to rule out unit tests, integration tests, and F5 step-through debugging with Rider and Visual Studio. This approach isn't even worth trying. And the reason why is that clearly this bug was something that users could reproduce, and the one piece of data that we did have, we had two pieces of data from all of them. They're all using Akka.NET 1.5 with distributed data, so we knew what settings they were using. And they always reported that this issue usually happened either after a deployment or a period of instability inside their network. So we knew that this probably meant having to cycle through nodes in the Akka.NET cluster. That means nodes joining and leaving. So F5 step-through debugging will not work with that. The reason being is that launching and shutting down processes over and over again using, my hands to try to do that simply cannot produce the timing and the consistency necessary to reliably reproduce this bug. On top of that, when we try to go ahead and suspend a process when hitting a breakpoint, that's going to go ahead and cause all of the heartbeat systems and all of the other processes to go ahead and begin failing. So it's going to have a really nasty observer effect that will make it, basically will invalidate the results of the experiment, more than likely. So the F5 step-through debugging approach was a loser right out of the gate. Unit tests and integration tests. Obviously, we already had a whole bunch of infrastructure that supported this, that attempted to test for these problems. And, I reviewed some of the racy tests. So we had some racy tests around things like cluster singleton handoff. But those issues came down to like stupid timing problems related to the way the test itself was designed. It never caught anything that looked like a duplicate inside of there. And why would it? We were never explicitly trying to do that before. So we decided to go ahead and settle on a new approach for trying to debug this issue: automated smoke testing. And the idea behind smoke testing is that rather than having, let's say, assertions and a testing framework for doing stuff, what you're basically doing with smoke testing is you're running something in a live environment or a live-ish environment, and you're going to do it with the full complement of observability. Logging, metrics, tracing, and alerts. You're going to go ahead and have a full telemetry setup designed to allow you to play back the tape. So in the event that something interesting happened while your test was running autonomously behind the scenes, you can go back and check it out later. So the other reason why automated smoke testing was a good fit for us was it allowed us to do like scientific variable sort of incrementation and parallelization as well. So this meant that we could go ahead and change one variable at a time inside our reproduction application, run multiple versions of the experiment, each in its own Kubernetes namespace, as we'd eventually do. And we could go ahead and compare the metrics, traces, and logs for each environment and see, did changing this variable have an impact at all on the design of the test, on the performance of the test, and whether or not I was able to reproduce our failure condition. The other thing that made this valuable is that smoke testing can run itself. You don't need to have a software developer sitting there looking at an IDE in order for it to work. Think of it like a slow cooker versus using a stove. I can go ahead and set it and forget it with a slow cooker. It'll go ahead and cook itself for 8 hours, and I can go back and check the results when I'm back home again. Versus if I have a meal I'm cooking right there on the stove, I got to stand there and do stuff with it the entire time. Well, we were thinking in terms of like how many man hours would it take to get to the bottom of this problem, and how many attempts would it take to reproduce this issue. And I said, look, if this issue is easy to reproduce, our customers probably would have figured it out by now. Obviously, it's not. So we're going to have to come up with something that will allow us to exhaustively attempt to reproduce this problem. Therefore, having the experiments automatically running themselves behind the scenes was the best and most economical way of trying to achieve this result. The other thing we were going to need to do is write some custom telemetry for duplicate detection specifically. We were not going to be able to catch this using clever logging statements or log aggregations. One of the really great strengths of Akka.NET and the actor model overall is that it makes it possible to query the live state of your running system while it is actually running and as it's changing. That means that it should be really easy for us to build some custom telemetry that can subscribe to all of the actor activations that are happening in each of the processes that are participating in our test cluster. And we can have all of that data streamed back to a central Singleton actor that is tasked with looking specifically for duplicates. So that's one thing that we were going to write. We also knew, in order to make sure we didn't waste our time chasing ghosts, meaning chasing down false positives, we needed to have a second method of verification that we had successfully reproduced the failure. So our second method of verification was going to be Pettibridge's command line tool for Akka.NET, Pettibridge.command. We have a cluster sharding command palette built into Pettibridge.command that allows us to do a diagnostic dump of every single shard region in the cluster and all of its shard allocation. And the thing that's valuable about the system is it aggregates the shard allocation data from each of the endpoint nodes, not from the coordinator, which means that if there's a duplicate, that'll be readily apparent in the output from this command. The other thing we had to do is when you're writing automated tests, particularly ones that run themselves with no human supervision, you have to have a reliable stop condition, which means that the experiment stops doing stuff once we know we've achieved the result that we're looking for. And in the event that that result holds steady, that we base there in, let's say, a equilibrium where let's say in this case, we find a duplicate and the duplicate stays there. That's when we know it's time for us to stop the experiment. We want to freeze it so a member of my team can hop in, run Pettibridge.command on it. Maybe we can go ahead and pull some other data out of the system while it's still running and see that that duplicate is definitely alive in multiple locations. Finally, after this occurs, we need to be able to work backwards on the telemetry data and understand where some of the potential bug fixes would be inside the system. So this is the approach that we came up with, and this is remarkably different than how we have historically done quality assurance on Akka.NET up to this point. The reason why we even considered doing any of this is serendipitously investigating another bug that we had fixed a couple weeks earlier. One of the things I decided to do while our office manager was away on vacation was take up a corner of her desk that she doesn't use and put a little test laboratory on it. And this is what our test lab looks like right now. We're actually in the process of expanding it, and we're going to get a real rack system for it. This is just what I threw together in a week by myself. But what we have in our test lab is we have basically a ARM64 and an x64 Kubernetes cluster designed to run a variety of both continuous experiments and one-off experiments. The continuous experiments are there for measuring things like idle CPU utilization. What's the background radiation of Akka.Cluster when it's not actively doing anything other than running itself? This is stuff that we need to be able to measure, and you can't really do that via an automated test. So the test lab was designed to help answer questions like that. So we have 2 Raspberry Pi 5s. This is the most recent edition of it with 8 gigs of RAM, and then they're each tied to an external 1 terabyte SSD. One of these Raspberry Pi units powers our telemetry systems. We run Seek, Grafana. We also used to run .NET Aspire on there. We got rid of it because it was using a lot of resources, and honestly, it wasn't very helpful in being able to look at data that's in there. We also run Prometheus. We have a Prometheus cluster actually where there's one Prometheus aggregator on each of the other nodes, and it streams its results back to our central Prometheus node running on RPI1, this Raspberry Pi unit right here. Then our big cluster, where we're going to run all of our cluster sharding experiments, is a brand new System 76 Meerkat. That's what this mini desktop is. And it has a 5 gigahertz. I don't remember what the brand name is for this, but it's the most recent generation of Intel hardware. It's a 16-core CPU and it has 64 gigs of RAM. So this thing was designed to be maybe it was 16 virtual CPUs. I don't totally remember. I'll have to go and double check that. But this is basically the setup that we had in our test laboratory environment. All of this was connected together, and apologies for this. You probably can't see it with the layout of my webcam. But basically, this is all connected via a Tailscale network. So we use Tailscale as our corporate VPN. Both myself and the other developers on our team, we can SSH into these instances. The Kubernetes clusters are also connected via Tailscale. So we can use things like GitHub Actions to do continuous deployment onto here. So I'll talk a little bit about our reproductions library, and then I'll show you some of that code in just a second. We have a reproduction library. Basically, it's a GitHub repository that contains lots of different pre-built experiments that all have standardized Akka.NET and Phobos. Phobos is our commercial open telemetry integration product for Akka.NET, which was, by the way, absolutely essential in finding this bug. We basically have a standardized configuration that all of these experiments use, and they're all designed to be fully parameterized via Microsoft.extensions.configuration. This is how we change the one variable at a time, is through this Microsoft.extensions.configuration system. And then finally, we have all these Kubernetes files, one per each experiment configuration. We had basically designed it so that each version of the experiment would have a control and then would have variations of it. All of them would run in their own Kubernetes namespace. And that Kubernetes namespace would get annotated to all of the telemetry that we would ship back to our log aggregation system, to our tracing system, and to our metrics system. All of that telemetry would get annotated with the namespace, and this allowed us to filter by experiment really quickly. And we'll see some of that data in just a minute. Lastly, we also designed it so our tests could automatically be redeployed using GitHub Actions and the Tailscale component for GitHub Actions. I'll go ahead and show some of this in just a moment. So let's go ahead and actually dive in to what the test laboratory environment looked like, and then we'll take a look at our reproduction sample. So what I wanted to show next here is the test lab itself. This is the environment that we're going to try to use to reproduce this problem. And I just want to go into it real quickly. I don't want to spend a huge amount of time on it, because what we're going to get into next is our theories that we had to actually put to the test. But this is our test lab one-off repository. It's private because we're connecting to some private resources like our virtual private network our Tailscale network that we go ahead and run all of our experiments over. We also have connections to things like our private NuGet server internally. In fact, I can actually pull that up. This is hosted in our test lab environment. This is our private NuGet server. Basically what we use this for out of all the infrastructure in our test lab is if we have like beta versions of Akka.NET that haven't been merged in yet, where we're trying to just figure out like Maybe we can add some extra debug logging to Akka.Cluster.Sharding and see if that gets us some better information on like why this bug's happening. We don't necessarily want to have to merge that into the actual real Akka.NET development branch and deploy it in a nightly build or anything like that. So this allows us to go ahead and deploy private builds like this version, Akka.NET 1.5, 274. That's not going to get deployed to Akka.NET, not going to get deployed to NuGet anytime soon. So we basically have connections to a whole bunch of private resources like that. It's one of the reasons why this repository is locked down. The basic way it's designed is we are using a whole bunch of .NET tooling to try to have some standards for how we produce experiments and how we're able to go and operationalize them and deploy them into our test environment. So the first thing that I've got right here is we have our little shared branch. This shared branch right here contains, well, not shared branch, but this is like our shared libraries. These are things that are shared across multiple experiments. And probably the most important is our shared configuration, where we have, let's say, this standardized Akka.NET configuration right here. And basically what it's doing is it's reading from Akka hosting. So I'm not going to get into all the details on that, but this allows us to parameterize a lot of different little facets around Akka.NET. We use Phobos, this is a proprietary library that we sell. And this is our open telemetry integration for Akka.NET. Now, this actually does a lot more than just add basic metrics and traces. It also includes some pretty sophisticated noise control, and it also integrates pretty deeply with some other componentry inside Akka.NET in order to try to get us better information on things like how many shards are active in the cluster at any given time, and on which nodes are they distributed. So this is a little bit of like a custom config we have for controlling how Phobos is configured. That's what this is. And then the other thing that we built for this experiment specifically is I went ahead and built this duplicate detector. So the duplicate detector comes as a standalone server. This is what aggregates all the data to try to detect duplicates. And if I go and pull this up real quick, we have a little duplicate detector server. I'm not going to go into all the details here. In fact, actually the better thing for me to look at would be the duplicate detector state. Here we go. So let me zoom in on this. So we basically, for every unique address in the cluster, so every single member of the cluster, we have a node state object. And we have a member history. It tells us what happened to this node in the cluster. That way we can track down restarts and other things like that. And then most importantly, we have the ability to keep track of a list of duplicates where the actor's a sanitized path is the key. And then the value is all of these sets of nodes where this actor was found. And this actor state object can tell us what type of actor this is, how long has it been detected at each of the two nodes. That can help us measure a duration for how long this duplicate might have been active. So that's basically what we're keeping track of. We also have this duplicate detector client, which basically, let's see, maybe even better than showing that code. Let's take a look at the experiment itself. Let's go to our experiment for duplicate shards. Program.cs. Let's see, actually, I guess it's the configuration is probably what I want to look at. Yeah, here we go. So we have this duplicate detector client that we add. So we add the duplicate detector client, and we say we're interested in all actors that start with this path. So any actors that appear after this path here, these are the ones where we want reports coming in about whether or not they're duplicates. And this configuration will be able to figure out like which node in the cluster we need to route this traffic to. We have Akka.Cluster.Sharding.delivery built into this, so we're not going to lose messages. The whole system's pretty robust. And the rest of these is basically, this is all parameter support for being able to go ahead and control a bit about how our experiment runs. The other thing that we've got working on this experiment is, in fact, it might be a useful idea for me to pull up one of our environments here. So let me grab K9s. This is what we use for Kubernetes. All right, so here's what we can see so far. We have several different environments here. Let's take a look. Looks like a couple of these environments, looks like this environment's not attempting to run any crashes at all. These other environments are in a state of crash loop back off right now. That's normal. What's happening here is that we have this node right here, this shard host 0. This is the one we want to take a look at. Duplicate detector 0. This duplicate detector, if I go ahead and use my petabridge.command pal on here, let's do cluster show. I can see there's only 2 nodes up in the cluster right now. So the experiment's kind of waiting for Kubernetes to pull some of those pods out of crash loop back off before it runs again. But basically, this duplicate detector always runs inside the cluster, and this node never gets exited as part of the reproduction. What it's going to do is we're going to listen to nodes joining and leaving the cluster. So we subscribe, right, using the cluster. We're going to subscribe to notifications about what's happening. So we get member removed events and all this stuff. And I won't go through too much detail on the code, but basically what this actor does is it's going to evaluate based off of the current state of the cluster whether or not we need to try to force the coordinator to move. Now I'm going to get into why we cared about that in a second. But if the coordinator needs to be moved, we're going to tell that node to exit the cluster is what's going to end up happening. And as that node starts exiting the cluster, other nodes in the cluster are going to get a notification that that node's exiting, and they're going to try to message it. This is an important detail that we'll circle back to once we dive into our theories about what could be causing this duplicate. But that's what the sort of experiment infrastructure looks like. Let's go back to taking a look at GitHub Actions. We have basically for each experiment that we're running, so we've got some for cluster clients, some for socket leak stuff. This had to do with an Akka management bug we fixed a while ago. Some stuff for testing Akka.Persistence health check with Azure table storage. And then finally, we've got our duplicate shards experiment here. So we have a specialized branch, this EXPR dupe shards. And what's going to end up happening is we're going to connect to our tailscale cluster. So we're going to use OAuth to go ahead and connect to it. And this is going to have us create an ephemeral tailscale endpoint. And this endpoint will disappear once the GitHub action finishes running. We're going to configure tailscale to connect to our Kubernetes cluster running on our x64 machine using kubeconfig. Using kubeconfig. So we're going to go ahead and connect to it. We're going to delete the previous experiment Kubernetes namespaces here, and I've got to manually kind of list all those out right now. We're going to then build our experiment Docker images. We're using the built-in .NET Docker SDK, which makes this really easy. So we're going to go and publish some custom images to our test lab. So I'm publishing one for, I think we've got 3 different images we have to publish. One's a shard region, one's a shard region proxy, which we aren't really using very much. And then finally, we have our duplicate detector, which is the thing that has all the custom telemetry on it. We're going to go and publish all those to our local Docker registry that's running in our test cluster. And then finally, we are going to deploy all of these Kubernetes files that are defined inside the experiment. And again, I won't go through the details of everything that's happening in here, but basically we're creating a namespace, we're creating a service account and some roles so we can use Akka management service discovery to dynamically form a cluster if we want. And then we publish a service for our shard host here. And then finally, we have our stateful set, which is going to reference this most recent version of our experimental image. We'll always pull the new version of that image when everything starts. So this allows us to go and make sure we're using the right version here. And then all these environment variables, these all map with the exception of these ones. These are open telemetry variables. But with the exception of those 4, the other ones all map to Microsoft.extensions.configuration values. And this is where we can do parameterization. So for instance, I can parameterize how many shards are in this experiment. How many entities do we have total in this experiment? How many entities per burst are we going to attempt to message every time we do a scheduled tick inside this application? And then what's the messaging mode we're going to try to use to communicate with these entities? Are we going to do it directly from the shard region? Or are we going to use a separate process like a shard region proxy and try to message it that way? We can also configure things like our telemetry settings here if we want to. So this is how we're actually supporting parameterization. And then finally, we have our duplicate detector, which is, right here. We're only going to run one of these. I got some parameters for that. And I could do things like disable the shuffler from running if I want to. So this is all kind of what we got running behind the scenes as far as infrastructure and code goes. The code isn't really that important yet for this bug. This is the infrastructure we're going to try to use to do smoke testing. And this is how we're going to set up the ability for us to scientifically alter one variable at a time. Now, if I go to our Grafana dashboard for our test lab, we've got a number of different ones here. This is the default Phobos dashboard. And this is over the last 6 hours. Let me change it to the last 15 minutes. So you can see here that we've had some nodes joining and leaving. And let me have this auto update every 30 seconds or so. So what's going to end up happening is we're going to have on average around a 3 to a 4 node cluster, but the cluster shuffler is going to be continuously trying to get nodes to leave in order to create a duplicate. This is the built-in Phobos dashboard. So this is the stuff you get out of the box whenever you install Phobos. So we can keep an eye on basically how much logging activity is happening. We can see how many actors are throwing exceptions, not very many. Actor message throughput's pretty low. We can see how many actors there are at any given time. This correlates roughly to actor starts and stops. We can see how many actors of each type there are. And then we can take a look at message throughput and message volume by type here. And we can also take a look at sharding statistics. Now, this is the duplicate detector, so there's only one instance of this. If I go to the shard host, we'll see a lot more messaging. Yeah, we'll see a lot more messaging around some of these various actors that are running here. And we can see a lot more actor starts and stops, but there's not a lot of throughput happening in that sample. I can flip over to one of the other experiments here, where it looks like there's not a lot of messaging traffic happening right now. Let's see why that is. Yeah, it looks like there's not a lot of message traffic happening there. Take a look at this experiment. Not a lot of message traffic happening there either. These experiments are basically all kind of in maybe a pause state. If I take a look at K9s again real quick. And yeah, it's because we have a bunch of stuff in crash loop back off. This is what happens when we keep having Akka.Cluster leave these processes over and over again. Kubernetes thinks the pod is unhealthy and is basically going to park it for a while. So that's what's going on there with this system. So this is our basic infrastructure we had to kind of set things up. The other component that we used real heavily is Seek, which is our log aggregation system. Now we're running all of this on a Raspberry Pi, and it's collecting, if I take a look at our ingestion system, about 205,000 events per minute. So, we're running this on a fairly small piece of hardware. And this also means that indexing might be behind by as much as 15 minutes. But if I go and take a look at, let's say, our dupe shard seed nodes namespace, and I look for host shard messages that have been sent over the past day, we'll go ahead and run this query real quick. And here we go. I can go ahead and see a whole bunch of host shard messages right here. And if I dig a little bit deeper into some of these traces, this is all Phobos data we're looking at, by the way. If I dig a little bit deeper into some of these traces, I can see the entire histogram of everything that's going on. I'm not 100% confident if I do that right now. Everything will be indexed, so it might time out on me, but I'll give it a quick try anyway and see if that works. Now, the last thing that we did that's super useful is, in addition to having Phobos' built-in telemetry, we wrote some custom telemetry as well. Let me see if I can find that. This is our duplicate detection system right here. And let me do the last 15 minutes. So it looks like the duplicate detector isn't even tracking any actors in the control namespace right now. My guess is everything's down for the count right there. If I take a look at our seed nodes namespace, I can see that we're tracking about 60 actors. And if I go to our other namespace, I guess that was seed nodes delay I was looking at first. We only have one tracked actor. So none of these experiments are in very healthy shape right now. So one thing I'm going to do, I'm going to go ahead and cut here real quick. I'm going to redeploy all the experimental versions of our little lab experiments here, and we'll take a look at some of the data coming out of those in just a minute. But first, why don't we go ahead and take a look at basically what some of our theories were about what could be causing this duplicate sharding bug. So these are the three theories that we're going to look into. There were actually a larger number of theories than that. Some of them ended up overlapping a little bit, and some of them we ended up ruling out really quickly. But these were kind of the three main ones. The first was a faulted handoff, that basically when we were rolling out updates to the sharding system, that it was possible for a handoff to happen. The old node never gets the signal that the handoff's complete, keeps its old shard alive, and the new home of the shard also starts up concurrently. So the shard exists in both places. We were able to really quickly rule this one out, but I'll get into it anyway. The next issue that we looked at was a distributed data sync issue, and I'll go ahead and do a little diagram of this. But the basic idea behind this is that there's a coordinator on the exiting node. So the coordinator is being shut down as part of this theory. The coordinator has to basically pass off a whole bunch of synchronization data about all of the shard rebalancing that it's doing while it's in the process of exiting. And it's flushing its state using the replicator from distributed data. We don't have any videos on DData right now. We'll get some in the near future. But the basic idea behind this is that we have these like little CRDTs, conflict-free replicated data types. And the structure that we use for Akka.Cluster.Sharding is what's called a last write wins register. It is possible that another write can come in from another coordinator that can overwrite what was previously there. And so in the event that a new coordinator starts up without syncing and capturing all of these shard allocations that the old coordinator made, we could end up with this sort of split brain where you have multiple shards running simultaneously. This was a lot closer to the real issue, but not for the reasons that we thought. The other thing that we thought about was, what if this isn't a rebalancing problem? What if this is a shard allocation problem, which is a little bit different? The shard allocation process is what happens the first time we are trying to allocate shards inside a cluster. Now, shard allocations can happen basically as a result of not all the shards in the system. If you have a large shard count, not all the shards might be fully deployed at the time a coordinator is exiting. This is especially true, ironically, if you're running a smaller cluster with lower message traffic. A large cluster with really high message traffic, much less likely to have this problem. But in this case, it might be that duplicate shard allocations were occurring where the coordinator was allocating shards to two separate nodes as a result of a distributed data sync issue. So these were kind of the first three theories that we pulled on. And these are the ones that we investigated. So I'm going to pull up our investigation document here and talk a little bit about how we eliminated some of these. So let me go ahead and grab that next. So what we're showing you on screen right here, this is how at Petabridge we deal with really complex bugs. We have to open an engineering investigation, and we have to write out all of the theories on what could cause this problem, and then we have to use the process of elimination to try to systematically work them until we basically distill it down to the last remaining couple of theories of what could cause it. And this is basically a way of helping software developers organize their work, because for problems of this class, they're too big for you to fit into your head, even if you are an exceptionally gifted programmer. You've got to write things down, and you've got to reason through them, and you've got to have a place for basically documenting what you did. The other reason why we want to write stuff down is so another software developer can help you work the problem. If you keep it all in your head and don't share it, you might as well take a pile of money and set it on fire, because that's basically what you're doing for the organization. You're basically siloing all this information all in one place. So we try to maintain journals when we're investigating really difficult bugs. The rule that we use is if you can't get it done in one sitting, investigation documents got to open. So we thought we were able to reproduce the shard handoff problem, which is basically, just to recap it, it's where we're rebalancing a shard from one node onto another, and we forget to terminate the actor on the original process that it was on. Well, deductively, this problem actually can never occur that way, and the reason being is that this problem only happened when nodes were leaving the cluster. That's one of the consistent observations that was noted across all of our customers. So basically that shard handoff problem we're describing here can only occur when we're scaling the cluster up and nobody's getting shut down. If a process is being shut down, those shards are going to be rebalanced, and the old process that was hosting the original shards will be terminated by the operating system. So there's no way basically for that problem to occur that way, but we did our homework anyway. So we thought we'd reproduce this problem. We added a couple new nodes to our Kubernetes cluster, and we noticed that duplicates occurred on old nodes in both of the scenarios. And, I started tugging on the thread here, and I decided to go ahead and use Seek's powerful capabilities to take a look at how many nodes basically received a begin handoff. This is the start of the shard handoff process, and how many begin handoff acts were sent. I noticed that on every single node where we had a potential duplicate, there was a corresponding number of begin handoffs and begin handoff acts, which means that this problem could not happen during handoff. Now, I noticed that shard host 0 had 0 acts, and it was because that was an in-memory message. So that was basically running on the same node where the coordinator was. And so my query string basically would not have turned it up. That's why. If I adjusted that a little bit, I was able to go and figure it out. Long story short, after basically gathering all this data from Phobos, this is all Phobos tracing data that we're looking at, we were able to determine that everything added up correctly, even on the nodes that were restarting. We noticed this node had 173 instead of 174 total acknowledgements. Well, the reason why that happened is that node was dead during one of the handoffs. So, it's not going to observe that. But otherwise, everything added up. So we were able to rule out the duplicate shard issue coming from the actual handoff system. We also did a thorough review of all that code and accounted for all the ways the handoff happens there, decided that this was pretty robust. The problem could not have occurred here. So the next bug or theory that we're going to look at is the distributed data system for Akka.Cluster.Sharding. This is the most popular mode of being able to keep track of how the sharding system allocates shards. So what's DData? It is an in-memory replicated, eventually consistent data structure system inside Akka.net. It leverages a special type of collection, or really a special set of types known as CRDTs, conflict-free replicated data types. I'm going to show a diagram in the next slide that kind of illustrates how these work a little bit. But the basic idea is that you can have a replica of a CRDT that has a unique identity of some type. That CRDT can be modified in multiple locations in the cluster and then merged together to form a unified view of how that data structure works. So you can have, for instance, we have sets, dictionaries. We also have what's called registers, counters, flags. These are all different types of CRDTs we support. Well, if you had, let's say, a set, you could do things like add 2 items on node 1, add the same 2 items on node 2, and on node 3, you could add an item, maybe delete a 4th one, and then merge them all together, and you'd end up with a unified view of what all that data looks like. Now, CRDTs do come, and this is an important detail, do come with some trade-offs. Namely, the big trade-off they support is that some of them don't support operations that normal vanilla collections do. Good example, a lot of them don't support deletes. Instead, what you have to do is use what's called a tombstone instead, which is a way of injecting a placeholder value that says there used to be a value here, but now there isn't. And the reason being is that the system can't reason about conflicts in the event that records can get deleted. Now, other types of CRDTs will support deletes, but they might have another trade-off, such as they might be subject to lossiness, where you can actually end up overwriting data under some conditions. So there's different trade-offs at work here with each of these. Akka.Cluster.Sharding uses this to keep track of shard placements using a CRDT called a last write wins register. And we'll take a look at that in a moment. Let's take a look at basically how DData replicates. And this is actually an important detail for understanding the bug that we're trying to get to the bottom of. So this publisher, in this case, this actor, this is our coordinator in Akka.Cluster.Sharding. Each of the nodes that has a shard region on it has a copy of the replicator. The replicator is what's responsible for keeping track of all the writes that are being done to these CRDTs. So when a publisher writes data to, let's say, an observed removed set, this is a CRDT that functions like a hash set, essentially. Well, if I add A to this observed removed set with this key, the replicator will go ahead and stream that delta to each of the other replicators in the cluster, who will then publish that operation back to all of those subscribers that are interested in knowing about changes to that observed removed set. And the replicators will write back acknowledgments to the original replicator, letting it know that we have received your update. This is sort of the basis for how distributed data works in Akka.net. Now, if we take a look at, let me pull up the Akka.net code from Cluster.Sharding, we use what's called a last write wins register. This is basically a way of replicating like a single value. In this case, it's a single version of our coordinator state. And a last write wins register basically means that the newest version of this data will always overwrite whatever was previously there. So that's basically how this data structure operates. Everyone has the exact same copy of what's in the register, and the newest writes always win. This means that this can potentially be slightly lossy. If you have competing writes coming in from multiple nodes, you can end up with an inconsistent view of how the state is supposed to look inside the system. And so basically what the last write register kind of does is it trades a little bit of lossiness in exchange for being reasonably performant and being simple. That's basically how this operates as a CRDT. This is the sort of issue that we're taking a look at here. This is the last write wins register. This is the state that we're going to end up replicating. And then if we take a look at the way we talk to the replicator, let's go ahead and look at the update function for this particular actor. Let's see. There it is, update. Okay. This is where we actually work with a replicator. So when we receive an event of some type, this event could be a shard being allocated, a shard being rebalanced, a shard region being activated, all the different grammar of events that the sharding system cares about. What we're going to do is we're going to tell the replicator that, hey, we want you to update this last write wins register Here's basically the new value that we're going to go ahead and pass in right here. Actually, the new value is this event that we're going to do. We're going to add this event to our last write wins register right here. So we're going to go ahead and update the previous value. And we're going to write this with a write consistency of, let's take a look, either write all or write majority plus. So distributed data supports tunable consistency, meaning that we could support a very low level of consistency, which means we might do only a local write, and we're going to rely on the replicator gradually syncing that value later. That makes our writes really quick when that happens. In the case of the sharding system, we're actually using a stronger consistency measure for both reads and writes. So read all means that every single replicator, if I pull my diagram back up, every single replicator has to agree on the value when it's being read. So they're all going to compare version, basically vector clocks. That's how they version the data. They're all going to compare vector clocks, and if they all come back the same, they will go ahead and return that value. If someone has a value that disagrees, the read operation might time out, and a read repair might happen where basically a sync occurs between all the replicators, and then you have to do the write again, and then you'll get agreement that time if that occurs. On the write side, it's kind of the same process, but in reverse. When we are using the write all consistency setting, every single node has to acknowledge the new value as it's written or the operation fails. Write majority plus and read majority plus, which are usually what we roll with by default, means your write majority means at least 50% or 51% of the cluster has to agree on what the new value is. Write majority plus means at least half the nodes in the cluster plus an additional n. And that additional n is usually like an additional 3 to 4 nodes. So this is basically a fairly high consistency setting for being able to make sure that everyone agrees on what the value is in the cluster. There's no way that if these settings are used, you can basically end up with an inconsistent view of the data just by having a new coordinator start up and read who else is there. There's no real way you can kind of lose data given the mathematics of how the read majority plus and the write majority plus are involved. So then if the fundamental consistency of how we're reading and writing isn't the issue, the timing of when we are reading and writing would be the problem. So if we take a look at our waiting for update function, and we're taking a look at how shard home allocations work. Let's see, waiting for update. Let's grab that. So what happens here is that when we receive, let's say, a shard home allocation, which this function doesn't really apply because we weren't using remember entities in any of these customer scenarios. What happens is we send the update to the replicator, and then we shift behavior to this waiting for update state, and we pass in the event that needs to be acknowledged by all of the other nodes before we can move on. So let's go to this waiting for update behavior right here. We are going to make sure we receive an update success from the replicator before we move on and do whatever we're going to do after the update's complete. This update success can only happen in the event that the write majority plus operation successfully was acknowledged by a sufficient number of parties inside the cluster. If that didn't happen, we would get an update failed or an update timeout message like this, which would indicate that the operation failed and the coordinator might kill itself or it might repeat the operation until it succeeds. There's various strategies we can use here. I guess we only kill ourselves if we're already in the process of terminating. So that wouldn't happen here. So the update success operation has to come through before we execute whatever this callback is we're going to do down below. So let's see what that callback would have been in the event of a shard allocation. If I go back to waiting for update, let's take a look at this. One usage, DData shard coordinator update. I guess I got to take a look at the shard coordinator itself. This is the base class here. The DData shard coordinator is kind of an extension of it. Well, I'll look for shard home allocated. All right. So here's what's going to happen. After the update completes successfully, we are going to execute this function. And this function is going to have us update our in-memory state. We're going to log that the shard was allocated at this location. And this is the important part. This is where we're going to send the host shard message to the shard region. This is what actually creates the actor that's been duplicated. So a really important detail here. We don't send that shard home message, that host shard message, until after the DData operation has successfully completed. Well, if that operation is successfully completed, and we know based off the consistency settings that a new coordinator that spins up is going to be able to read everything that was already there, and we also know that the old coordinator, in order for it to actually allocate the shard, has to get a full acknowledgement back that its write was processed. There's no way we can lose data as a result of the coordinator shutting down in the process of doing this. This operation would just fail and the shard would never get allocated. Therefore, there would be no duplicate. So we were able to rule out that problem too. It can't be a matter of the consistency settings of how the distributed data system works. So this leaves our third theory, which we'll take a look at next. All right, so we had eliminated 2 out of the 3 theories. So we knew that it couldn't be rebalancing. We knew that it couldn't be a DData consistency issue, but that still left us with the possibility that this was, a duplicate shard home allocation, particularly as the coordinator was leaving. So what we decided to try doing was basically really pull on the thread of this duplicate shard home allocation. We did some review of the code, and we decided that the most likely explanation for how there could be a duplicate shard allocation, given all of the careful acking and knacking involved, was we realized that the shard coordinator and the shard region, that's the actor that creates the shards, were the only 2 actors involved in the shard home decision making. So there was kind of this isolated communication channel between the 2 of them, and that the replicator for distributed data, the replicator was basically only, since we're using a last write wins register, whatever data was being written by the coordinator would usually fly, even if there were competing writes coming in and out from potentially a second coordinator. So our new theory of the case was that there was a brief period here where there could be 2 shard coordinators, both independently making shard home allocation decisions at the same time. Now, we didn't have any evidence pointing explicitly to this, but in terms of what could cause the shard home allocation problem that we were pretty fairly certain was happening, and bear in mind, we still hadn't reproduced anything yet at this point, we decided that this scenario seemed like the most likely explanation for what was going on. So we were going to redesign all of our experiments to constantly force the shard coordinator to move. That's why when I showed K9s a little while ago, you could see all those crash loop backoffs on our pods. That's from the cluster shuffler, the component that we invented to do this. That's from it basically trying to kill the coordinator over and over and over again in order to force it to move. The next thing we need to do is attempt to allocate shards aggressively when the coordinator is exiting. So basically, we got to ring the dinner bell. When the coordinator node starts to exit, we're going to go ahead and make sure all the nodes in the cluster that do messaging to individual entity actors start really trying to allocate shards basically when this happens. So the dinner bell gets rung whenever a node starts exiting inside this design. The cluster shuffler is going to basically stop once duplicates are detected. So once we see the duplicates are detected, we're going to stop trying to move the coordinator. That way, myself or another team member, we can pull out Pettibridge.command and some of our other diagnostic tools and actually poke and prod the live version of the experiment where we reproduce this so we can try to get some more information about what might have happened. And in the event that we had, let's say, a false positive, we had some mechanisms in place that would basically clean up fake duplicates. So good example, if a node failed to report that some of its actors shut down because the node itself is terminating, the cluster, whenever it would publish a member removed event, that would cause those duplicates to get cleared out of the detection system. So if I flip over to our chart real quick, this is what our experiments look like right now. We're using a version of Akka.net where the bug's fixed. So you see here that we've got several thousand tracked actors, but no duplicates. And if I flip over to this environment, you'll see that we only have 4 tracked actors right now. That's probably because everything's in crash loop back off, if I had to guess. But this number will surge back up into the thousands again in the not too distant future. When we had real duplicates, and I'll show you a picture of this in just a moment, when we had real duplicates, we have this chart here, duplicate duration, which measures how long have these 2 duplicates been active. Entity actors automatically shut down after 2 minutes. So you'll see basically a big surge in the number of duplicates, and then it'll tick down after a couple of minutes. That's because the shard shuts its entity actors down if they haven't received a message after a couple of minutes. Our experiment is designed to stop messaging once coordinator nodes aren't trying to exit anymore. So the only duplicates that'll be left will be the duplicated shard actors themselves. And you'll see this duration will just go up and to the right in this sort of staircase function when we actually do find one. So let's go ahead and take a look at some of the investigative work we did to try to figure out Could this be because of duplicate shard coordinators? Now, you can see on our Notion document right here, this is our testing matrix, and these are all the different variables we can run. So basically, like message shards after member up, message them directly or via proxy. How do we form the cluster? Is the cluster shuffler enabled? Does the cluster shuffler work by forcing a node to leave or by downing a node? What's the pause between shuffles? What's the cluster size, shard count, entity count, etc.? This doesn't really match what we finally had when we reproduced it, but this is sort of the direction we were going in. We got our first successful reproduction after being at this for like 3 weeks. So it took forever for us to reproduce it, but it finally happened. And we were able to go and pull some of the actor hierarchy logs from all 3 of these nodes. So I used Kubernetes to basically run kubectl exec to get all this data. And we were able to go ahead and take, okay, we know that shard 852 is running on host 1 and host 2. Let's go ahead and double check this in the actor hierarchy data, which will do a printout of the cluster. We'll also do a printout using the cluster.sharding data. And I was able to confirm that the actor was alive in both of these processes. So we knew at this point that we definitely, for real, had a duplicate. Now let me scroll down just a little bit. Here we go. This is that little staircase function that I was talking about earlier. This is what the system looked like when we were able to successfully reproduce this issue. We found 40 duplicates, so this means 20 shards got duplicated and were found in 2 locations in the cluster. And the duration for the duplicates, this is just going to keep going up and to the right until I shut the experiment down. So it was going to go ahead and continue on forever, basically. And so we knew that this was legitimate at this point. So we were able to reproduce the bug. And the way we decided to do this investigation is you want to focus on a microcosm. Rather than trying to look at a giant distributed system with tens of thousands of pieces of concurrent activity going, focus on one thing and work backwards from what happened to that one thing. Try to tell a mechanical behavioral story from the point of view of something that's like atomized inside your system. So in this case, we did a query in Seek for what happened to this entity. This would be shard. Well, what happened to this shard, shard 929? And we produced a timeline of basically where this actor got started. And I had to work through some of the Phobos tracing data on Seek to do this. But we basically discovered, in this time frame, this is like 20 seconds apart roughly. So shard 929 is allocated on shard host number 2 by the coordinator running on shard host 0. And then 20 seconds later, shard 929 is allocated for a second time on shard host 0. But here's the interesting piece. It's a totally different coordinator who allocated it. And shard 929 was never rebalanced. So it was alive in both places. So this confirms the duplicate shard home allocation theory here. And we could see it in the Phobos trace data sitting inside of Seek. So I went ahead and I wrote like a little breadcrumb trail of what might have led to this. Because bear in mind, we see that there's 2 different coordinators involved, but we're still not sure on the timing yet. So we see that shard host 0 is the coordinator, gets the signal to begin exiting the cluster, and shard host 1 becomes the new coordinator, and shard host 0 allocates another shard 1. This is the smoking gun right here. We have 2 different coordinators alive at the same time. Now, this is the theory I put together, but we can actually see this getting reproduced inside some of the events here. So that's the theory. That basically that the new coordinator, and by the way, because the reason why we think this is that cluster singletons get promoted when the old cluster singleton is exiting. That exiting phase doesn't mean that the actor's dead yet. It just means that that process is imminently going to be terminated once it finishes doing all of its cleanup. So there is a brief window in theory where you can have a brand new coordinator on one node and a dying coordinator on another node, and those 2 are out of sync. Therefore, that's how you could end up with these 2 different duplicate shard allocations. Now, if I take a look through some of this data right here, we basically have our time frame here working from, let's see, the older data. Shard host 2 gets reported as member up. So this is basically what happens here. Shard host 0 gets reported as member left. Then it gets reported as member exited, gets reported as member removed. And the second shard allocation, actually, you know what? I think I've got a better set of reproduction logs. I got a lot better at doing this after about the 4th try. If I go down to, let's see, successful reproduction number 3, here we go. So I've got sort of a better set of data here. We see that this duplicate shard got allocated by shard host 0 at 42 seconds. And then at 28 seconds, shard host 1 got that same shard deployed onto it by shard host 2. Okay, so when did the coordinator start on shard host 0? We saw around the 27-second mark, about a second after this shard got allocated. No, actually about a second before shard host 1 got allocated by shard host 2. We saw that the coordinator on shard host 0 became the new singleton. So that happened like a second earlier. On shard host 2, we basically didn't complete handing over until about 30 seconds or about 10 seconds or so after the other coordinator had already been promoted. So what this data shows us right here is that there's a 10-second window where there's a coordinator alive on both nodes. And we were actually able to verify this using some of these seek queries to go ahead and kind of show when the shutdowns began in both of these locations. This led me to, so basically we could see here that there was some inappropriate behavior occurring. And here's the reason why that inappropriate behavior occurred. Let's see if I can pull up this permalink right here. So this is the permalink from this reproduction from July 23rd. And this is, if I take a look at my notes here, this is basically shard host 0 trying to become oldest. So what we see here on shard host 0 is we basically see that shard host 1 has apparently, well, actually we see a member exited event right here. Now this member who's exiting is actually shard host number 2. But the logs right here show that we think it's shard host number 1. Shard host number 1 was the previous coordinator before shard host 2 stepped in. So this is after like the third iteration inside our cluster shuffling. We can see down here that shard host 1 receives a handover to me message from shard host 0. And this is the bug right here. When we have two different cluster singleton managers, one of whom believes it's becoming the oldest and the other one who believes that it's shutting down, what's supposed to happen is the node that is in the becoming oldest state. So if we go back here, the becoming oldest state node messages the was oldest node and performs a handover. When that handover completes, the singleton is dead on the old node and alive on the new one. Well, here's the problem. The old node was shard host number 2, and shard host 0, who is basically thinking it's becoming the next oldest, is messaging shard host 1. Shard host 1 just restarted maybe about 20 seconds prior to all of this. And basically it gets that handover message and it assumes, I must have previously been the coordinator. I have no record of that, but I'm getting a message from this other node telling me to hand it over. So I'm just going to automatically acknowledge it. And in fact, we can actually see that code if I go to Akka.Cluster.Tools and I go to the singleton down here. If I go to the younger behavior, when we're in the younger behavior, this is the state that we're in when there's an older node than us present as the cluster singleton manager. When I get this event, this oldest changed event, indicating that one of the previous older cluster singleton is shutting down, I'm going to check to see, am I becoming the next singleton, or is it someone who's even older than I am? And that's basically what we're looking at in this code right here. Well, what's interesting is while I'm in this behavior, if someone sends me a handover to me message, see this comment right here. This node was probably quickly restarted with the same host name and port. This is exactly what a stateful set does in Kubernetes, which is where we're reproducing it. We're going to go ahead and confirm that the old singleton instance has been stopped. And so we reply that handover done. And this is what causes the new singleton to start up a lot earlier than it's supposed to. The wrong node was messaged. And we can see that in the trace right here, that shard host 1 received this handover to me message from shard host 0. It should have been shard host 2 that was contacted. So this leads us into the bug. Why did this happen? What could have caused this problem to occur? Well, let me go ahead and pause real quick, and we will take a look at some of the source code inside Akka.net and talk through the two different bug fixes we eventually had to make to fully resolve this issue. So we'd basically determined by looking at that Phobos trace data that this is where the problem occurred. When we see this log message appear, oldest change, the wrong address was appearing here, which means that this oldest node, as it's reported inside the cluster singleton state, is not actually the oldest node in the cluster. It's a node that has somehow been restarted and hasn't been updated yet. So that is the fundamental problem. We are messaging the wrong node. And this is what happens here is we say peer, we go ahead and we pass in the address of that node and we tell it to hand over to me. And a node who isn't actually the singleton acknowledges it back. And therefore, for a brief period, we have two different singletons. And that's how we can get into this situation where there's multiple duplicate shards. So now at this point, we also know that the second bug about the singleton moving too early has to be related to this, if not the cause. We basically know that for certain now too. So the question is, why is this a problem? Well, let's take a look at this oldest change buffer to oldest change message, since this seems to be what kicks everything off. The oldest change buffer is an actor that's part of the cluster singleton system, and its job is basically keeping track of have older nodes in the cluster shut down. Heuristically, the way cluster singletons like to allocate themselves is they always want to stick to the oldest node in the cluster, oldest node of the appropriate role type in the cluster. And the reason why that is that if you're doing dynamic scaling, where you're scaling the system up and down, you're going to end up in a scenario where basically the nodes that are stable, that are always there, even when you've scaled down to your lowest possible size, those are going to be your oldest nodes in that environment. And we do not want to have to move singletons if we don't have to. Therefore, those are the best candidates for that. So that's why Akka.Cluster.Singleton kind of prefers to hang out on those oldest nodes. Well, what's going to end up occurring here is that the way an oldest node is determined, if we take a look at the code here, the way an oldest node is determined is by what's called an up number. The first node to join a cluster will be assigned an up number of 0 or 1. I don't remember which value we start with, but it doesn't really matter. The next node will get +1 added to that, and then +1. And up numbers can get reused. If you have, let's say, 30 nodes join the cluster and you scale back down to 10, and then you add another one, the up number of that new node will be 11, probably, assuming that everything was done contiguously. But you can never reuse an older up number. It's basically kind of like a way of versioning nodes when they join the system. So when you first join a cluster and you're hosting a singleton manager, whoever is older than you are when you join the cluster, they're going to be the only nodes that are ever older than you are. You can't have a time-traveling node in Akka.net. So that's basically what the oldest change buffer is keeping track of. Have nodes who are older than you begun the process of exiting the cluster. And so the way this works is that if I go to this method here, and let's take a look actually at our cluster event subscriptions here. So this is an untyped actor. We are going to subscribe to events in the cluster, membership events. And what's going to end up happening in our onReceive statement here is if we get a new member, we add it to our list. If a member gets removed, we remove it from our list. And if a member is exiting and that node is not us, we will also remove it from the list. And if it's us exiting, we're going to go ahead and basically acknowledge that we're in the process of shutting down, more or less. And then these messages right here, get next. This is basically how the cluster singleton manager communicates with us about keeping track of who's changing, from youngest to oldest inside the cluster. It's these member events that are interesting. In particular, it's the member exited event is where the trouble began. So what happens here is that when a node basically signals that it's exiting or it's been removed from the cluster, we go ahead and we check to see, does that node have a matching role with the one that we expect? And if it does, we go ahead and we basically track changes to members by age. Members by age is an immutable sorted set. We're going to remove that member from here. So what will happen is we'll compute who is the first member by age in this sorted set. And then we'll execute the block, and then we'll check to see who's the next member by age in the sorted set. And if the values are somehow different, this means that the oldest node in this list has changed. And we will then queue that change up, and that change will eventually be disseminated to this method right here, where we'll receive it, the oldest changed event. So this is where the trouble began. So the thing I decided to look at is when you're trying to eliminate a really challenging bug like this, look for the stupidest thing first. So the first thing I decided to take a look at is the sort order of this collection. So yeah, that's pretty good advice. Always try to eliminate the stupidest thing first. This is the member age comparer, and we create this immutable sorted set using the with comparer member right here. And the first thing that I notice is that we're asking for member age, member ordering descending. Small problem with that. The oldest nodes are sorted in ascending order. not descending order. So this means that this is backwards. So I decided to take a look at the sort order function here. X is older than Y. So if we are in descending order, this will be false, so we'll return -1. So if X is older than Y, we return a -1 here. So it's named descending. Let's go ahead and check to see if that's correct. Well, in Akka.Cluster, we actually have a member age ordering because this is also how we do, let's see, work with the split brain resolver inside the system. So let's take a look at that. And there should be an age comparer. Here we go, age comparer. Let's see how this works. This age comparer, we'll check to see if A is older than B, we go ahead and we return a -1. So if the left is older than the right, we return a -1. So I took a look at this. If X is older than Y, left is older than yet that. And let's see, if we're in ascending order, we go ahead and we return a 1. If we're in descending order, we return a -1. So this is a scenario where it's kind of like two mistakes at like a fast food restaurant cancel each other out. You order a double quarter pounder with cheese, and the person making it writes it down as a Big Mac by accident, and so they go ahead and submit the order wrong. But the person who's filling the order picks up a box that says Big Mac, and someone accidentally put a double quarter pounder with cheese in it. So by the miracle of two different accidents, you end up getting the right result at the end. This is basically what happened here, which is that descending order makes it sound like this is happening in the wrong direction, but that's actually not the case. This is actually happening in ascending order, but thanks to what I can only assume is like a dyslexic error right here, the person who implemented this actually got the sort order wrong down here. So in addition to getting the names mixed up, they also actually got the direction you would need things to be in mixed up as well. So this member age comparer actually did end up working correctly. I ended up deleting this code and having it just use the member age comparer that's down here. That way we only had one implementation. So there's no do not repeat yourself style mistakes happening here. But that was definitely a potential source of problems. So that was one issue we fixed and took a look at, but that ended up not fixing the problem. We were able to still reproduce it after that. And that's because the age comparer actually did function correctly after all. So what else could have caused this problem? Well, another thing I noticed down here is the data. This is a finite state machine actor in Akka.NET, and a finite state machine basically has a combination of state data that it's in, and it also has events like messages that it processes as well. Well, I noticed that the state data that we have is a mutable collection, and that we are doing things like inserting data to the front of that mutable collection, and we're going to go ahead and pass that back to ourselves as the next state, and we're also potentially copying some of that mutable data from someplace else. Now, I did go through all this code and was able to validate that we did not have a mutability issue, like as far as I could tell. That was obviously there. But nevertheless, I changed this alt in the final fix to go ahead and use an immutable collection just to take that away as a potential hazard. So we've implemented 2 fixes so far. Bug is still here. So what else could be the problem? Why is the wrong node at the front of this list? So where does this list come from in the first place? Let's take a look at that. Well, this list gets populated, not the handover done I want to take a look at. It is, let's see, initialize FSM. When we first start up, we start the oldest change buffer actor right here, and we wait. We basically wait for it to give us the initial oldest state. And when we get the initial oldest state, we check to see, am I the oldest? Can I immediately go ahead and become oldest? So we'll check that out. Otherwise, we'll check to say, okay, if it's not safe for me to become the oldest, and it's not safe for me to be the oldest when like other nodes are in the process of shutting down. That's basically what that boils down to. But otherwise, if I'm the oldest and it's not safe, I'll enter the becoming oldest state. This is not a code path where the bug occurred in the system. We know the bug occurred down here. This younger, basically going to state younger using this initial oldest state. And what we would do here is we would filter this list for all the addresses that were not us. And so the oldest address at the front of this list would be the oldest node in the cluster. This find all method does preserve order, so we didn't have to worry about any weird shuffling or anything going on there. Now, if I scroll down into the younger state, this oldest node, this node 1 that we saw, in our reproduction. That was still the oldest node on the list, even though it had left the cluster like 15, 20 seconds earlier. It was a fast restart, basically, is what happened. So I was thinking, okay, so there's a reason why we get this oldest change method, but the oldest change that prompted this list, this node, the thing that triggered us to get this oldest change message, so node 1 had left a while ago. It was node 2 starting to exit is what caused us to receive this message. So the node that caused us to receive this oldest change message was not the same one at the front of the list. What could cause that? What could cause that problem? Well, as it turns out, when a member gets removed, this is when we're fully purging a member's history from Akka.Cluster. I noticed this little method right here, schedule delayed member removed. And bear in mind, this is code that's been here for about 10 years. In fact, if I look at the git blame, let's take a look at this. This code goes back to, let's see, 2015, 2016. It's been around for a while. So it's pretty old code, not quite 10 years, but it's been around for a bit. The removal margin, if it's greater than 0 seconds, we go ahead and we schedule this delayed member removed to run in about whatever this value is. And after some digging, turns out this value is 20 seconds on average. That would be an important piece of data, as we discover later. The reason why this is important is when we're in this youngest state, let me scroll back up to it, or really in any state, when we get that member removed, we do not remove that member immediately from our list. But when the delayed member removed comes in here, in fact, let me just keep going. Yeah, younger, here we go. When we get this delayed member removed, we go ahead and remove that node from our younger data. So that node is no longer at the front of the list. So the problem was occurring because we were rapidly forcing the coordinator to move inside our system, and we're forcing it to move under that 20-second threshold. That's what was causing the problem. And by the way, this is like an original design error that was in the original Scala Akka and is still there, and is an original implementation error in Akka.net. So the real problem was a data consistency issue. This oldest changed event could be happening in response to a totally different node leaving the cluster. Meanwhile, our snapshot of who's older than us is actually out of date by about 15 to 20 seconds. Therefore, we're going to signal the wrong node for a handover when this occurs. So here is how I ultimately fixed this. And by the way, getting to this realization took like 70 hours. Oh, not 70 hours, probably about 65. The other 5 hours are spent verifying the fix. If I go to our development branch, I've refactored this code a bit and stylized it a bit more. But if we go back to our younger state and we take a look at the oldest change message, we'll see that we now have two properties. I also added support for nullable while I was at it, just to eliminate, I found some potential bugs that could have caused as well. But basically we have the previous oldest and the new oldest now. We are keeping this data from the oldest change buffer to signal who is the new oldest and who is the previous oldest. So when we receive this, we check to see, okay, are we the newest oldest? All right, looks good. And we take a look at the younger data to oldest.head on there. All right, see if that all looks good. And basically, if all of the other younger nodes have all been removed, we're going to go ahead and try to go to oldest. All right, that looks good. This is basically consistent with what we were doing before. Here's the real fix. We're going to go ahead and take a look at the previous oldest. And if the previous oldest is not null, it can be null in cases where we're the first node to become the singleton. We are going to make sure that the oldest change gets added to the front of that list. And that way, when we go and message a node for a handover, we're now talking to the correct node. So in other words, this is a data freshness issue. We're going to make sure we get the fresher data from the oldest change buffer and use that instead of whatever's in our state. Because that delayed removal function was added there in order to try to basically make sure that in the event that a cluster singleton ungracefully left the cluster as a result of, let's say, the network fragmenting and the split brain resolver having to kick in and remove unreachable nodes, this is designed to basically give that node some time to gracefully shut down when we weren't able to contact it. Well, the problem is that that compensation mechanism created another bug in kind, which is that in the event that nodes are restarting rather quickly, we're using the same address, we're communicating with completely the wrong party. And we're also getting the wrong idea on basically like who should we be talking to right now. So the easy fix for this was, when in doubt, use the data from the oldest change buffer and ignore this sort of more potentially stale data that might be stored in our actor state. We could probably go through and refine this design even more if we wanted to, but that's the basic big idea behind this, is that we should make sure that these two different pieces of state are really talking about the same node. So I'm going to wrap up with a couple of conclusions, but this was the big fix. This is what took forever to find. And we went ahead, and if I go and take a look at our duplicate detection system, we have probably moved the coordinator tens of thousands of times with constant reproduction since then and haven't been able to reproduce it. Whereas normally when we did have Akka.NET code that had the bug, once we were able to figure out how to reproduce it, we could reliably reproduce it within a couple of minutes usually. Now we can't. So we know that the bug fix was stable. And I'm going to go ahead and wrap up with a couple of conclusions. Okay, so I just wanted to go ahead and wrap up this long story with some conclusions. The first was that the biggest misnomer that caused us to waste so much time was the coincidence with this bug being reported shortly after Akka.NET 1.5 shipped. This made us think that it had to be something we introduced in 1.5. So as it turns out, the technology changes we made actually stabilized and improved cluster sharding to a significant degree. That's why people started using it more. So ironically enough, it was the fact that 1.5 made the technology more robust, and Akka.Hosting, which you can learn more about in a video in our description, the fact that Akka.Hosting came out and made the technology much easier to use, popularized it, got more people using it, and that's what exposed the bug. The other thing that I'd mention is that more and more of our users have probably gotten better about using open telemetry and using log aggregation and real APM systems over the past several years. That probably also helped contribute to finding the issue. A lot of customers that use Akka.NET and really any technology in fairly scarily large applications still use utterly ancient monitoring approaches. I mean, we're talking like IIS logs and power grep. I've still seen that used as recently as like a couple years ago. So I think the fact that modern observability practices have made some inroads with a lot of people in the Akka.NET community, I think that's another reason why this bug got found finally, even though it's been there for 10 years. This code dates back to 2015, 2016. The other thing that we learned, smoke testing absolutely works. The advantage of it is that, look, this thing was able to find reproductions while I was out at dinner, while I was asleep. It was able to keep working long after I stepped away from my computer, which was great for my sanity, but it was also much more efficient for being able to do that. The other thing was leveraging Phobos and open telemetry, which I'll touch on at the very end here, allowed us to kind of keep all the data and play back the tape and see what happened. That plus designing the experiment to use a reliable stop condition to basically stop doing stuff and try to keep the experiment in stasis, that was super useful as well. Variable parameterization works. So being able to scale up and down the number of shards, the amount of actors we were messaging, the ability to turn the shuffler on and off, the ability to change how the shuffler worked, all of that was necessary to eventually reproduce this problem. So this is basic science, is you isolate one variable, add another version of the experiment that changes it. And if you want to have multiple experiments changed, or multiple values changed, you do what we do, which is we ran multivariate experiments. And, you know, if you have enough horsepower in your telemetry system and in your Kubernetes cluster, you can do that quite easily. We're definitely going to invest in more hardware for our test lab directly as a result of this, especially we need something more powerful in a Raspberry Pi with a 1 terabyte SSD to process all the logs that we produce. And then finally, OpenTelemetry plus Phobos for the win. It was really Phobos' built-in tracing that made it possible for us to find this bug. Specifically, it was able to capture all of the logs that were recorded when actors were processing messages. It was also able to go ahead and capture all these detailed system messages that were keeping track of things that were happening behind the scenes. And there's no reason you can't activate any of that inside your own application. So you want to learn a little bit more about Phobos, I'll include a link in the description here, but definitely recommend doing that. We're going to talk probably a bit more in a webinar in the not too distant future about how to leverage Phobos for these things. But anyway, I want to thank you all for your time. I hope you found this entertaining. This was a long story to tell, but I enjoyed doing it. I enjoyed giving a chance to kind of show you a little bit what goes on behind the scenes here. We've never really talked that much about debugging before, but this was the nastiest bug I've ever had to solve. I'm really glad it's fixed. It's available now in Akka.NET 1.527, this bug fix. Please go and upgrade to that if you're a user. Otherwise, please don't forget to like and subscribe and get notifications. Thank you very much.